It's 20 past now. When's the... All right, good time to start. Awesome. Good afternoon, everyone. How's everyone enjoying NDC Sydney so far? Having fun? See a couple of thumbs up? Yeah, woos. Awesome, fantastic. That's good to hear. My name is Velida, and in this talk, we're going to talk about implementing scalable messaging patterns in Azure. Now, just a show of hands in the room, how many of you have worked with Azure? All hands, fantastic. That's what we like to see. How many of you are building kind of like distributed architectures, working extensively with different messaging services? Less hands, well, more hands. Yeah, come on through. Cool. So today, this session's it's really intended to go a little bit deeper into some of the patterns that we can actually implement using different messaging services in Azure. So if you have that foundational knowledge, I think I was chatting to a couple of you beforehand, like you're in the right place, great. We're not going to touch too much of the foundations. We're just going to actually go a little bit deeper and try and see what patterns and problems we can solve using different messaging services in Azure. A little introduction of who I am. I'm a lead software engineer at Mental Group, based out of Melbourne. I used to live in Auckland, but I moved to Melbourne last year, and it's great to be on this side of the Tasman. Melbourne's great, love it. I'm former Microsoft MVP and Microsofter, but my primary experience, I've been a .NET developer, working in a variety of different industries, from banking, agriculture. If you live in New Zealand, you're going to meet a couple of farmers here or there. Writing code for them is something I didn't think I'd ever do, but here I am. And also the health industries and also health insurance as well. So a little bit of a round of experience. A former average rugby player as well. I used to be a lot bigger than this, a little bit chubbier, but yeah, now I don't need to run into people. I now just bash my head against the screen when my code doesn't work. So today, we're going to start off with a little bit of what the difference is between events and messages. I know that's a really foundational question. I have had a lot of conversations over my career chatting to architects, software engineers who may get confused between the two concepts. And then we're going to cover the messaging services available in Azure, the difference between them and what purpose they serve. And then we'll start diving into some of the problems we might face when we're architecting systems and dealing with messages within our architectures, and how we can actually implement patterns to solve those problems. Finally, just go away with a few takeaways. So messages versus events. There's an important distinction between services that deliver events and those that deliver messages. So to take a step back a bit, events are really lightweight notifications that kind of indicate to us a condition or state that's been changed. When publishers publish events, they don't have any expectation on how that event's going to be handled. They essentially say, something's happened, off you go. And then the consumers of that event will essentially say, okay, we're going to decide what we want to do with it. Events can be discrete or as part of a series. So discrete events are really events that report state change and they're actionable. To move on, consumers only need to know that something happened. It has that information, but not necessarily the data that triggered that event. And then a series of events are events where we can actually report conditions, analyze them. They're time-ordered and interrelated, and consumers kind of need that sequence of events to analyze what happened next. And then messages are really raw data produced by a service to be consumed and stored elsewhere. The publisher will have an expectation of how that consumer is going to handle the message. So there's a bit of a contract that exists between the two sides. So going into our first kind of Azure service, Azure Event Grid. Anyone worked with Azure Event Grid extensively or even a little bit? One hand. It was a very slow hand, very like, yes, almost reluctantly. No, just kidding. It's an eventing backplane that enables event-driven reactive programming. So it uses PubSub, where publishers will admit events, but have no expectation about how those events are handled. It's deeply integrated with Azure services, so I wouldn't be surprised if some of you who didn't put your hands up have actually used Event Grid, because a lot of Event Grid is used for a lot of Azure services in the back end. But it can also be integrated with third-party services. If you actually look at the payload of events that are sent by Event Grid, it doesn't contain the actual object that was updated. It just says, hey, something happened. So if a if a blob was created in Azure Storage, you get that event saying, hey, a blob's been created, along with some metadata like timestamps, e-tags, all of that stuff. It's available as PaaS on Azure, or if you're running Kubernetes with Azure Arc, you can also use Event Grid that way as well. Next is Azure Event Hubs. This is it's designed for big data streaming platforms and event ingestion services. It's really great for processing millions of events per second. It can capture, retain, replay telemetry, and event stream data, and that data can come from many concurrent sources. It's made available to various stream processing infrastructures and analytics services. So out in the wild, I've seen Event Hubs used extensively with Cosmos DB, Azure Synapse Analytics. It's really great for those scenarios where you've got millions of events and you want to analyze them. It's also great for low latency scenarios as well. So if you're working with millions of events and you need to process them quickly, Event Hubs is really good for that. They also come with a guarantee of at least once delivery. Now, Azure Service Bus is a fully managed enterprise broker with message queues and also pub subtopics. It's designed for enterprise applications. They're going to need transactions, message ordering, duplicate detection, and consistency. And when we're working with cloud-native applications, Service Bus provides kind of reliable state transition management for your business processes, making it really ideal for those situations where you have to handle messages that have extremely high value and they can't be lost or duplicated. It's also good for hybrid cloud solutions as well. I've been in teams in the past where we've kind of had to commute from on-prem to the cloud, and Service Bus can actually help connect those systems together. It's a brokered message system, so meaning that until consumers are actually ready to receive messages, Service Bus will store them in a topic or a queue. And it has advanced messaging features like first in, first out capabilities, batching sessions, transactions, dead lettering, etc., which will go into detail about how you can use these features within these patterns. You do get a guaranteed of at least once delivery with messages sent from Service Bus. Low battery, that's good. And the option for order delivery of your messages as well. Now, storage queues are really considered more a part of Azure storage rather than part of the messaging infrastructure, particularly from an Azure perspective, but they do provide that messaging functionality, so it's worth chatting about it. Queue storage is really designed for storing a larger number of messages, which you can access via HTTP or HTTPS, and these contain millions of messages up to around 80 gigabytes worth within a queue. We see Azure Storage being used in scenarios where you want to track progress of processing messages in a queue. So if you have a worker and it crashes and you need to pick up from where you left off, another worker could come in at that point and pick up those messages. It's also handy for when you require server-side logs of all transactions that are actually executed against your queue. So just from a high level, you can see that there's a variety of different messaging services that Azure provides, serving different purposes. Some work better for events, and then some are designed better for handling messages and for those enterprise applications. So some of the questions that we might ask ourselves when we're actually building our systems is, okay, are we dealing with messages or events? Are we reacting to events? Are we processing events? Do we need kind of those advanced capabilities like ordering? Do we need sessions, transactions? How many events and messages do we need to process? I've seen and have been in a couple of teams where we've used event hubs for something where maybe Service Bus was a little bit more suitable, and vice versa. And do we need to architect our systems to kind of handle events or messages? Are there parts where, okay, we just need to know something happened and we can go and react however we like? Or do we need messages for those kind of advanced features? And as I kind of continue and move on in my career, my best answer that I've had to every technical question is, it depends. This is kind of the it depends approach. You may find that you'll use multiple or different services together to fulfill different roles. So you may want to link all these services together to kind of create data pipelines. So something might happen within an Azure resource. You might want to capture that with Event Grid and process that and send that event to Event Hub. It's important as we go through some of these problems and patterns that I'm going to talk about today to realize that it's not one size fits all. There are different services in Azure that serve different purposes. Awesome. So that's kind of just like a quick tour of Azure messaging. So what I'm going to do now is go through some of the problems that we might face when building or architecting our applications using messages, and then just talk about some of the patterns that solve these problems. So the first problem we might have is when we're sending messages or events to different consumers is who's interested in this? So in distributed architectures, systems will need to provide information to other systems when stuff happens. And asynchronous messaging is a great way to actually decouple senders from consumers to avoid blocking senders to waiting for a response from a consumer. However, if we try to dedicate a consumer for each, or dedicate a queue, for each consumer, this isn't going to scale too well. Because you might have numerous consumers and then provisioning queues for each one of those consumers. That's going to introduce a lot of overhead, and it's going to be very difficult to manage. So we need a method of sending events to all who are interested, all the consumers who are interested, without necessarily knowing who they are. So this is where good old pub/sub really comes in, or publish-subscribe model comes in. Here we introduce an asynchronous messaging subsystem, where we have an input channel that's used by the publisher, and then we have an output messaging channel per consumer, which we refer to as subscribers. And so the mechanism for copying each message from our input channel or from our publisher to all of our interested subscribers is typically handled by our message broker. So when we think about this from an Azure perspective, we could have an Azure function that publishes messages to a service bus topic, and then multiple Azure functions could subscribe to that particular topic, and each subscriber will receive a copy of that message from the topic. So all from an Azure perspective, the consumers are really worried about is, can I subscribe to this topic, and then the publisher just posts a message to the topic without having to worry, okay, who are these specific consumers that this message needs to go out to? And with this, we actually get the benefit of kind of decoupling our systems that need to communicate with each other. If anything happens to a particular subscriber, we can use the message broker to handle the messages that can't be picked up. So if we're taking an example from a queue, if a consumer crashes for whatever reason, that message can stay on the queue. It can also stay on the topic as well. This pattern will also give us some control about how we process messages as well. Subscribers don't necessarily have to immediately pick up messages from the queue itself. We can pick up messages with off-peak hours or at a certain schedule. We'll talk a little bit about scalability and reliability under load in the moment, because there are different patterns that we can use for that. But essentially, deferring communication responsibilities to the message broker can take away handling the responsibility of handling load, the delivery of our messages, etc., and allow the application to focus on its core capabilities. Integration between these subsystems becomes a lot simpler, because all we need to really do is interact with the message bus. So a producer of a message doesn't need to worry about the semantics, about how the consumer is going to pick up the message. All its responsibility is really focused on is publish something to a queue. And then the consumer's like, I'll pick up something from the queue and then do the work. There are some things that we do need to keep in mind how we handle the subscribers. Ideally, we need to be flexible enough to allow consumers to unsubscribe from the channels when needed. We also need to keep security in mind as well. Who is actually authorized to listen to a queue or a topic becomes a point of conversation with your security team. If you're concerned about ordering and priority, we'll talk about some patterns in a moment that can handle that. But essentially, throughout all of these patterns, particularly this one, you need to start designing your systems to be idempotent to remove any dependencies on order handling if that's an issue. Handling poison messages as well requires a dead letter queue. So you can return the messages back to the queue if something fails, rather than causing your consumer instance to fail. So if something's not quite right with your message or it's malformed, having a dead letter queue that you can send messages back to will help prevent failures within your consumers. We'll talk a little bit about scaling, a little bit about how we can implement some patterns to actually scale out consumers, because there's some there are different patterns that we can use to do that. And then also communication within pub/sub is unidirectional, which brings us to our next pattern or next problem, is that do we need a response? There are some scenarios where you will kick off some work and will need an immediate response that something has happened or a message has been received. Now, we may have an API that gets an immediate response with a particular status code, so 200, 404, etc. And most of the time, the responses to those kind of calls are very, very quick. However, as part of that API call or whatever work that we're doing to initiate some work, we'll actually initiate background tasks that takes longer, so seconds, minutes, even hours. So in these situations, it doesn't make sense for us to kind of make the request and then expect and then to wait for a response, since that's going to be long background processing work. So a solution to this is really through async request and reply for HTTP polling. This is useful for client-side code, as it can be difficult to provide callback endpoints or use long-running connections. So here, a client application will make a call to an API that actually triggers the long-running operation in the background. The API will kind of send a response as quickly as possible. This is usually HTTP 202, so accepted, to tell us that the request has been received, and now we're going to kick off some processing. That response should hold a location reference pointing to an endpoint that we can poll consistently to check the status of that long-running operation. And in the background, this API will actually offload the processing to another component that will complete the long background processing work, such as a message queue. And then once that work is complete, the status endpoint can either return a resource that indicates, okay, this has been completed, or it redirects to another resource URL. So looking at how we could implement this in Azure, say we've got a client application that's making a call to an API, it will send a message to a queue that kicks off the background processing work. And then in the meantime, we have another status endpoint that's been provided through the web API. So to check the status of that work, we continuously poll that status endpoint, who will say, for example, this background processor is writing results to a blob storage. That status endpoint can query that endpoint to check for to see if that file has been written to storage. Now, some things to consider. With that initial accepted response, you should kind of indicate in the header, okay, where should I poll for the response and how long? So you should have retry after headers within your response, so consumers know, okay, where should I poll for location for the background work, and how long can I continue to poll this to make sure that the work's being done, and what progress that long status code, that status is. This is great for client-side code this pattern's great for client-side code where it's difficult to provide those kind of callback endpoints or long-running connections where it adds too much complexity. So it's not suitable for kind of real-time streaming scenarios or asynchronous notifications. And if your clients need to collect a lot of results and latency is important, this pattern's not fantastic for that either. Now, some of the messages we deal with in our architecture may be very large. So if you're working with images, sound files, these files these messages could be extremely large. Sending them directly to the bus is not recommended, because the larger your message is, the more resources, the more bandwidth you're going to consume, which can cause bottlenecks within your solution. Now, messaging services in Azure have limits on how big your message can be, because essentially they're designed to handle a huge quantity of small messages. So just having a look at some of the limits in Azure, you might think that if you have to deal with large messages now and then, you can just solve the problem by just scaling up. It's my boss's problem. He can pay for, or she can pay for higher tiers for our message broker. This isn't going to make you any friends. I know that from experience. Nor is it a practical way to kind of deal with large messages. So a pattern that we can use to kind of solve this problem is the claim check pattern. This is also referred to as reference-based messaging. And the solution here is to split your message into two parts, the claim check or a reference and the payload of the message. The idea here is that you store the payload of the message into an external service, such as a database. You get the reference of that message, and then you send that to the bus. This reference acts as like a claim check, hence the name of the pattern, and a consumer can use that to retrieve the payload from the data store. So this is really useful for when we do deal with large messages, and we don't want to send them directly to the bus, or we can't send them to the bus directly because they're too large. And it's also useful for situations where we want to authorize only particular services or a subset of our services to access the payload. So by offloading it to an external resource, you can apply stricter authentication and authorization rules in place to ensure that the payload is stored securely within the database. Some things to keep in mind when you're using the claim check pattern. If you don't need to archive the message payload, you need to think about how you're going to manage that particular piece of data and consider its lifetime. Do you want it sitting there in the database for any archival processes, or once your consumers have kind of done what they needed to do with the payload, do we need to delete it? So just think about data management there, save a bit of money and all that good stuff. Because we've stored the payload of the data elsewhere, there will be, you do need to consider the additional overhead and latency that external service involves. So because you've provisioned, since you're storing it in another database, it's essentially another resource that you actually have to manage. Now, you may not want to use a claim check for every single message that gets passed to the bus. You may be dealing with large messages once in a while. So you might want to include logic within your application to deal with messages that are too large for your bus. This is a conditional claim check as well. So you don't have to apply the claim check to every single message, just messages that are too large for your bus to handle. So prioritizing background processes. We touched a little bit on background processes earlier. In your architecture, there are going to be some tasks that are more important to deal with than others. The order in which requests are usually received aren't too important, but there are going to be cases within your applications where they'll have different priorities, so you need to process them faster than lower priority tasks. Now, priority could mean different things to different scenarios. It could apply to the task itself. If you're working with multi-tenanted systems, it could apply to different users or tenants of your system. So say if you've got some customers who have a premium subscription and you need them to process their orders quicker, that could be their higher priority customers compared to lower priority customers. It could be a mixture of the two. So this is where the priority queue pattern comes in. Now, queues work on a first in, first out basis, and consumers receive messages in the same order that they're posted to the queue. However, some queues support priority messaging. So essentially, your application, when it sends a message, will assign a priority to that message. And messages in the queue are then reordered so that those that have a higher priority are received before those that have a lower priority. However, in Azure, there's no native support for automatic prioritization of messages via sorting. So in Service Bus, this is where you can use topics and filtering on topics to kind of implement this. So using topics, you can create subscriptions that support queuing mechanisms that provides message filtering. You can use topics that an application can post messages to, and then within the metadata of that message, you can assign priority to that message. So you can say, this is a high priority message, this is a low priority message. And then that message can be filtered on within Service Bus, and then high priority consumers can listen to that particular subscription and do their processing work, and then lower priority ones would listen to lower priority. Now, you may think, or you may be sitting there thinking, well, isn't this essentially we're just adding more resources, this is more overhead, how are we going to manage all of this? This is actually kind of design, this is an intentional design from Azure. So this guy, Clemens Vastas, principal architect of messaging at Microsoft. Basically, I wrote a blog post about the priority queue last month, and he actually replied to me on this, where a queue with built-in priority sorting is not implemented by design. So Microsoft have really taken the approach that for higher priority tasks or tenants, we should separate out queues. So the analogy of kind of this they uses here about airport processing is that for higher priority messages, we send them to a dedicated queue, and we prioritize the processing of those messages. And this, depending on how you rank priority, the advantages to this, you can be a little bit more granular. You can assign different priority levels to your messaging. If priority changes over the life cycle of your application, it then becomes at the resource level where you can decommission some queues, introduce different priorities. Say if you're doing different offer types as part of a subscription, then you can kind of split your queues and subscriptions that way within Service Bus. So taking this approach, each queue will have its own kind of like separate pools of consumers. So you've got your pool of consumers for high priority messages and consumers for lower priority messages. And this allows you to be a little bit, be a little bit more clever about how you manage your pool of consumers. So your higher priority queues can run on a larger pool of consumers that run on larger hardware than lower priority consumers. So if you're low priority consumers, you could run on cheaper hardware, provision lower SKUs, and while your higher ones, you can dedicate more resources to. Another way you could implement this is to implement a single pool of consumers that check for messages on higher priority queues first. And then once those higher priority messages have been processed, you then start to fetch messages from lower priority queues once the higher ones have been processed. Now, with the single pool approach, you need to be a little bit careful because higher priority messages are always received and processed before lower priority ones, whereas here we've split the pools between different priority levels. You don't want to get into a situation if you couple all these pools together and you're just pulling messages from high priority queues that you don't forget to process lower priority queues, priority messages. So don't, if you're going to use a single pool of consumers just to read off the queue, just be mindful that your lower priority messages aren't just left on the queue, never being touched and never being processed. So really, when implementing a priority queue pattern, the questions you might want to ask yourselves when thinking about priority for your messages is, okay, do we assign priority to the type of tasks that we're performing? Do we have are we building multi-tenanted systems where we have users or tenants that are more important than others? With higher priority tasks, do we need to process all of them before lower priority tasks? If so, then maybe a single pool of consumers approach would work. If not, then we can start to kind of split our pool of consumers out to higher and lower priorities, and then think about what kind of infrastructure we're going to use to support those consumers. And then thinking about, so with that, we can think, okay, do we need to be clever about how we partition our consumers for priority, and what kind of infrastructure do we need to process those messages faster? So the next problem that we can really think about is handling a large number of requests. And this is where we're going to now focus a little bit more on consumers of our messages. So one problem we may encounter is handling the large number of requests that come through our system and how we can actually scale our consumers to handle that. Because rather than passing requests synchronously between services, we're now implementing a message queue to deal with requests asynchronously and to ensure that our applications don't get blocked while processes are ongoing, or processing of those messages is ongoing. Now, the number of requests that our applications receive can vary over time. So you might have peak hours where you're experiencing a lot of traffic or a lot of requests coming through, and other periods of time might be very low traffic and have to deal with low messages. The work performed by those tasks can also vary as well. So you might have to perform a lot of work, you might be doing simple tasks, etc. If we have a single instance of our consumer, we can run into situations where it becomes flooded with requests, or even the messaging broker itself might be overloaded with messages. Now, one approach that we could take to kind of handle this is we could run multiple instances of the consumer, but this is where we run into challenges of making sure that they are coordinated so that a single message is delivered to a single consumer. We also need to consider how we're actually going to load balance across consumers to prevent a single instance becoming a bottleneck to our entire application. So the answer to this is using the message queue to kind of implement a communication channel between an application and an instance of a particular instance of a consumer service. So this is what we refer to as competing consumers pattern, where applications will post requests in form of messages to the queue, and then instances of our consumer service receive messages from the queue and process them. So this approach allows the same pool of consumers to handle messages from our message broker from any instance of the application. This is a little different from PubSub, where all consumers will get passed every single message. In competing consumers, each message is passed to a single consumer. Now, with Azure Functions and Service Bus queues, we can actually implement this pattern really easily using triggers and bindings in Azure Functions. So Service Bus enables consumers to use peak lock mode when it retrieves a message from the queue. So what this does, it doesn't remove a message from the queue, but it hides it from other consumers that could be attempting to read from the queue. So the function's runtime will receive the message in peak lock mode, and if the function successfully executes, it completes the message. But if the function runs longer than the peak lock period, you can essentially add a timeout period to the peak lock duration on your message. That lock is renewed as long as the function is running. Now, those of you who have worked with Azure Functions before, we can actually scale in and out based on the depth of our queue, and multiple instances of that function can independently pull and process messages from our queue. So what we achieve with the competing consumers pattern is the ability to use the messaging queue to act as a buffer between our producer and consumer and use it to kind of load level the variation in volume of requests. We also get the benefit of improved reliability since we aren't sending messages to a specific consumer. So if that consumer instance of that consumer fails, the producer isn't blocked from doing further work, then another instance of our consumer service can actually pick the message up from the message broker. We also gain the benefit of scalability here, as consumers are able to dynamically scale as the volume of messages increase. For transactional read operations, we gain a little bit of extra resiliency. Should we read and process messages as part of a transactional process and a particular instance fails, we can use the competing consumers to ensure that messages are actually returned to the queue so that another consumer instance can come along and pick it up. If you're running into situations where your messages are continuously failing, my recommendation is to utilize dead letter queues to actually return that message to the dead letter queue. It could be a poison message. It could be a number of reasons. If a particular message is failing for multiple reasons, it's better just to send it to the dead letter queue rather than sending it directly to the queue to try and pick up over and over again. Now, the order of messages that are received aren't always guaranteed. So idempotencies will be important to factor in here. So if a consumer fails, we need to actually minimize the effect of processing a message more than once will have. Malformed messages and poison messages may cause our instances to fail. So like I said earlier, we need to ensure that those messages aren't returned to the queue so a consumer instance picks up and you just have all these consumer instances failing. You need to return that message elsewhere, such as a dead letter queue, so you can analyze it and see what's going on. Now, because with this pattern, there's no direct communication between the producer and the consumer, if we need to resend a result back from our consumer to the producer saying, yes, this message has been picked up, you're going to need a mechanism or a way to actually do that that's accessible by both. So in Azure, what you can do, you can use worker processes to send results back to the application using a dedicated message reply queue. but this does require correlation of the message between the two. Now, for scaling, we need to be mindful of messages overwhelming a single queue. In some cases, what you can do is you can actually petition your broker to send message from specific producers to specific queues, or you can actually distribute messages across multiple message queues. So that covers kind of scaling from the consumer side. Those situations can be quite complex to handle, particularly when it comes to actually petitioning consumers of our messages. And these design choices aren't really trivial, because the more consumers you have, the more orchestration is required, the more queues, the more complexity. If you find that your workloads are a lot simpler, just introducing a single queue can actually help level the load between application instances and other resources that are going to pick up messages from that queue. So taking the following example here, I've got a bunch of app instances that are performing heavy writes to Azure Cosmos DB. For those of you who've worked with Azure Cosmos DB before, if I say what a 429 error is, you'll be familiar. That's essentially too many requests. So we're essentially what our heavy writes are doing. They're overwhelming that resources with concurrent requests. So what we can do here is implement a queue to kind of level the load between our application instances and the data store itself. So we read messages from the queue and then perform the write requests from a single instance. Now, the trick to be mindful of here is how the consuming service processes messages coming from the queue. We need to implement logic that kind of controls the rate that we pass requests to the data store. Otherwise, all we've done is taken the problem from our producers and pushed it further down the line and added a queue for no reason. So as you can probably guess, implementing this logic to actually handle the rate that messages are being sent needs to be tested to make sure your resources aren't overwhelmed. So that may introduce the need for more queues and instances to handle your volume. So you can test that by doing some performance tests on that to validate if your application logic is going to be able to control those requests being sent to the data store. That's going to be required. Again, if you need a reply from your service to say, hey, this message has been processed and it needs to send that to the consumer, you're going to need to implement that yourself. And depending on how much load you actually experience, you can run into situations where your system is always queuing up more requests than you're processing. This is where you need to be mindful of the persistence capabilities of your queue, because you don't want to lose information if your queue isn't your messaging broker isn't able to persist messages that are sent to the queue. For whatever reason that your queue crashes or drops information, messages will be lost. And then auto-scaling can introduce some interesting problems in this pattern as well. So if there's increased contention for resources that services share, that can effectively cancel out the effectiveness of using the queue to level the load. So let's talk about ordering. So often when we are dealing with messages, we'll need to process a sequence of messages in the order that they arrived, while still being able to scale out under the increased load. So a good example is if you've bought something online, you might have paid for the order, you want to track the order, is the order delivered? And these all need to happen within a sequence. And in distributed architectures, this isn't always straightforward because workers will scale independently and pull messages independently, like we talked about in the competing consumers pattern. So the way that we can solve this is using a sequential convoy pattern, where we push related messages into categories within the queuing system, and then have the queue listeners kind of lock onto that category and only pull messages from that category one message at a time. Now, in Service Bus, there's a feature called Sessions that we can use to provide concurrent demultiplexing of interleaved message streams while preserving the guaranteed order delivery. So essentially, a session receiver is created by clients once created as accepting a session. When the session is accepted and kind of held by a client, that client holds an exclusive lock on all messages with that session ID in the queue or subscription. It also holds exclusive lock on all messages with the same session ID that will arrive within the queue. So with the lock, We can renew it should we need that session to stay alive. But once we no longer need that session, we can close it and discard of it. So think of the lifetime of an order. We can keep it that session associated to a particular order ID. And then once that order is completed, it's delivered, we're happy with what we bought, we can close that session because we no longer need it. So thinking about this in a practical sense in Azure, we can implement the sequential convoy pattern using sessions, and our consumers can utilize the peak lock functionality to receive messages from that particular session. So using our order tracking application, we process each ledger message in the order that it's received, and then send each transaction to another queue where we set that category to the order ID. That transaction doesn't span multiple orders, so consumers that process that particular order can process, or consumers that process orders can process each category in parallel, but in a first-in, first-out manner within that order. So our ledger processor function here takes care of processing the transaction one at a time, and then setting that session ID to the ID of our order. Our consumers will listen to the secondary queue where they process all messages with matching order IDs from that queue using peak lock mode. So in that kind of scenario, we used our order ID as the category. For your own scenarios, you need to kind of think about what property of the incoming message you can use and you can scale out on. And you should also consider how easy it is to add new categories of messages to the system. So using our ordering example if we needed to onboard a new customer, could we have a set of different processes that distribute the work for our different customers? For high throughput scenarios, we do need to think about kind of like a start and end property to the message. Do we need to sort it by time and then process it as a batch? If it's very high, if the throughput is very high, the kind of first in, first out requirements, we may need to consider that. And there's always, with this pattern, there's no guarantee that messages won't be received out of order. Because there's network latency, intermittent issues, those kind of cloud issues still exist. So one method you could use is kind of implement sequence numbers for your messaging to kind of verify the order of your message. Another thing that you could use is kind of a flag to indicate, okay, this is the last message of our sequence. This is the last one in our transaction. So we just put that within the message metadata to indicate that this is the last message. So our final problem, which we're going to discuss, is handling distributed transactions. Anyone here kind of handled or worked in scenarios where you've had to work with distributed transactions? Ish. Yeah, it's painful. One of the first jobs I had coming out of uni was working for a bank in New Zealand, where we were trying to build a payment system using microservices. Someone upstairs drank the Kool-Aid. Yep. And we had distributed transactions everywhere. And it was a nightmare. So talk about the good things first. Try and end the day on some positivity. So using microservices, having a database per microservice can provide the benefit for us at a microservice level. So if we have a particular domain that's going to particular data within a microservice that has various natures of heavy writes, heavy reads, whatever, we can use the best data store type and schema for that particular microservice. However, if you think of all your microservices using various different types of data store, trying to ensure data consistency across your architecture poses one or two absolute nightmares. And distributed transaction protocols like two-phase commit protocols require all participants in the transaction to either commit or roll back before the transaction can proceed. Not all database technologies, not all message brokers are going to support this. Another problem that we have, inter-process communication availability. So that the operating system provided IPC allows separate processes to share data. For all of your microservices to commit distributed transactions, all of those services must be available. And that's going to cause you a lot of sleepless nights. So one approach that we can take here, or the approach that we can take, is perform a sequence of local transactions using a Saga pattern. So if you think about all of your individual microservices, each local transaction will be the overall atomic work effort committed by a particular participant in the Saga. So each local transaction will update the database and then publish a message or an event to the next participant along, saying that the local transaction has been committed and you need to go and execute the next step. If a local transaction fails, so say on service B here, our transaction should fail for any reason, the Saga then executes a series of compensating transactions that undo changes that were made by the previous one in service A. And there are different types of transactions that we can actually implement within the Saga. So compensating transactions. So these are transactions that can potentially be reversed by processing another transaction with the opposite effect. We also have pivot transactions. So this is kind of the go, no-go stage in the Saga. If this commits, essentially the Saga will attempt to run until it's done, or it could be the last compensating or first retriable transaction within the Saga. So if we say no-go, we then try and retry all the different transactions that were made in prior participants in the Saga. And then retriable transactions are essentially ones that just kind of try to reverse the local commits made on prior local transactions. Now, there are two common implementations of the Saga pattern that I'll discuss today. So the first one is orchestration. So orchestration is a way to coordinate Sagas where there's a centralized controller and it tells the Saga participants what local transactions to execute. The orchestrator here will handle all the transactions and tell the participants which operation to perform based on events. The orchestrator will then execute Saga requests, stores and interprets the state of each task, whether it's failed or not. And if there has been any failures, it will handle that by using compensating transactions. And this is really good for situations where you have quite complex and complicated workflows, because you get control over every participant in the process as a central controller, essentially controlling every participant. If you have numerous participants, a good way to kind of handle all of them is via an orchestrator. There's no cyclical dependencies, and Saga participants don't need to know about other participants. All they're concerned about is what the orchestrator tells them to do. However, with that orchestration, there is additional design complexity that we introduce because there has to be coordination within the orchestrator to make sure that the workflow is being followed as intended. And also the orchestrator becomes the point of failure. It's managing the entire workflow, so it becomes a central point of your architecture that becomes the point of failure. So for more simple workflows, we can actually implement choreography. So here we coordinate Sagas where participants exchange events without that centralized point of control. So each local transaction will publish an event that triggers local transactions in other services. So a client, for example, a client could publish a request to a message queue, and then as messages arrive, they're published to subscribers interested in that particular message. Each subscriber will do its own thing and respond to the message queue with a success or failure of that particular operation. This way, the services, rather than relying on a central orchestrator, they'll actually choreograph the workflow amongst themselves without having to depend on that orchestrator or having direct communication between them. And this is really great for simple workflows that don't require that coordination logic. Because there's no orchestrator there, we don't require additional service implementation and maintenance of that orchestrator as well. So we remove that single point of failure, since now the responsibility for executing that workflow is distributed amongst all participants within the Saga. However, and this is one of the situations that we've kind of fell into or fallen into a couple of times, as your workflow grows, as you add more services into your architecture, adding more participants, the complexity increases. and it becomes difficult for your Saga to track what your Saga participants, what commands they're going to be listening to, what events they should be subscribed in, etc. Here, there is a risk of cycle dependencies between the Saga participants because they could run into situations where they have to consume each other's commands. And then finally, integration testing for this can be an absolute nightmare because essentially all services have to be running to kind of simulate a transaction. So the Saga pattern is a bit of a challenge to implement. So distributed transactions really require a new way of thinking. You're not committing a transaction within the scope of just one service. You're trying to achieve that data consistency across multiple microservices, which is kind of one of the reasons you should ask. If people say, we want a microservices architecture, you should be saying, why? Why do you need it? Do you actually need it? It's hard to debug as well. So as more participants are involved in the Saga, this only gets more challenging. This is where it becomes really important to implement observability and monitoring to be able to track the workflow of your Saga to see where the points of failure are, see things where things have gone wrong. Now, using the Saga pattern, data can't necessarily be rolled back because your participants will commit changes to their local databases. And your implementation has to be capable of handling a set of potential transient failures. So this is where idempotency comes back into play. It must try and design your services to be idempotent, to reduce the side effects, and to ensure data consistency. The lack of participant data isolation also imposes some durability challenges. There's a lot of things that can go wrong here, and you have to try and implement countermeasures to reduce anomalies like lost updates, dirty reads, non-repeatable reads, etc. So when we're starting to think about, okay, how are we going to design our messaging systems, some of the takeaways that I want to impart to you today is really start from the very basics. What are we communicating? Are we communicating messages to different services? Are we communicating events? Do we expect a response back? Or do we just want to tell our consumers, hey, something's happened, go and do some work? Then we can start to think about, okay, how can we break up our architecture using specific message brokers? Do we want to use something like event hubs to process millions of events? Or do we want Azure Service Bus so we can benefit from those kind of features that Service Bus provides? Think about the complexity of your architecture as well. A general rule of thumb is don't try and be too clever about it. Try and make it as simple as possible for the scope of what your application is trying to achieve. Is ordering your messages important? Is ordering an important factor for your architecture? And think about ways that you can design your application to do that. And also who's listening to messages and events as well. How are you going to manage scaling those consumers? How are you going to be able to manage the different variability in traffic that will come to your application? And then finally, you don't need to implement all of these patterns in one application. Some patterns are going to be more applicable than others. Some you won't need. Some will be too complex for what you're trying to achieve. So just think about what you actually are trying to achieve, and then think of a pattern that you can use to solve the problems you're facing. Awesome. Thanks for listening. I'm going to be hanging around until Friday. So I'm at the Mantle booth. If you have questions or you want to, Mantle Group, we are hiring. So, if you are looking for your next gig, come and talk to myself or a couple of others who are in the audience today. You don't have to follow me, but I do write about messaging patterns, Azure architecture, all the good stuff on my blog. So if you want to read some of the stuff I've done, feel free to do so. I'm also doing a lot of stuff on GitHub as well. So if you want to check that out, please do. Awesome. Thanks for coming.